Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
In this video, we're going to have a look at cabling and Wi-Fi, the Ethernet protocol, and network addressing. Hang around, you'll love it. When it comes to connecting devices, there are two options, wired and wireless. Wired connections have been around since the beginning of time. That's the late 1960s as far as networks are concerned. A wired network uses cables to connect devices together. Wireless technology in general has existed for a long time. Think of radios and mobile phones, for example. The wireless technology that we think of most with networking is called Wi-Fi, which has been around since the early 1990s. Cables can be copper or fiber. Copper cables are usually cheaper and are very common for short distances. Data is sent over copper cables using electrical signals. This means that they can be affected by outside interference. I'll explain why this happens a bit later. Fiber cables are made of strands of glass. Data is sent through the fiber in the form of light. Fiber is more expensive, but is really good over longer distances. Also, it is not affected by outside interference. A wired LAN uses a protocol called Ethernet. Remember that a protocol is a set of rules that devices in the network agree on. Ethernet is made up of a lot of different parts. Some of these parts describe types of cabling and the speeds that they run at. Other parts describe how the data should be formatted and sent. This is called media access control. The reason Ethernet is layered like this is so devices with different cables and different speeds can all still communicate. Imagine a workstation that has a 1 gigabit connection to the network. It wants to send data to a server that has a 10 gigabit connection. The workstation prepares a message. It formats it according to the media access control rules. Then, it prepares to send the message according to the physical rules that it has to follow. When the server receives the messages, it decodes it at the physical layer. The message that is left is the same as it was at the workstation's MAC layer. As you can see, even though they have different connections, the hosts can still communicate because of this layering system. Ethernet was designed by a group called IEEE. IEEE have created many different standards for different technologies. All of their standards have a code number. Standards that start with 802 are used for LANs. Ethernet, for example, is 802.3. Remember how Ethernet is a group of standards? Each of these is assigned 1 or 2 letters. For example, 10 gig Ethernet is 802.3AN. If you'd like to see a full list of Ethernet standards, have a look at the Wikipedia page on IEEE 802.3. Codes like 802.3AN can be tricky to remember, so each of these physical standards have friendly names, which are a bit easier to understand. For example, 802.3AN is also known as 10G base T. This gives us a bit of a hint about what the standard is. The 10G refers to the speed of the connection. In this case, it is 10 gigabits per second. Base is short for baseband. This means that it uses a digital signal. The alternative is broadband, which uses an analog signal. The T means that this is a UTP cable. I'll explain what a UTP cable is soon. You might see other cables here, like LX, which refers to a type of fiber optic cable. Electrical cables use electrical signals. These are a pattern of 1s and 0s. The receiver needs to decode this pattern. The pattern is called an encoding scheme. To send electrical signals, a circuit is needed. This means that electrical cables need to contain several wires. The most common copper cable is called unshielded twisted pair, or UTP. Modern UTP cables contain 4 pairs of wires, where each pair forms a circuit. electrical signals over copper cables can be disrupted by interference. Think back to high school science for a while. Do you remember that electricity and magnets are related? Electricity flowing through a copper cable creates a magnetic field. A magnetic field and a copper cable can create electricity. The problem is that a pair of wires running parallel create a small electromagnetic field. The field from one pair of wires can affect the signal on another pair of wires. This is called crosstalk. UTP eliminates most crosstalk by twisting the pairs of wires together. Each pair is no longer running in parallel, so they don't generate the field. If you can, find an old network cable that you don't need. Cut the end off it and strip back the plastic around the outside. You'll probably find 4 pairs of wires, depending on how old the cable is. There may also be a plastic core or a piece of string. They're color-coded, so each pair has a solid color and a striped color. For example, one pair will have brown and striped brown wires. Now I said that you will probably have 4 pairs. There wasn't always 4 pairs though. Older Ethernet standards, such as 10 base T and 100 base T, only needed 2 pairs. But to achieve 1 gig and 10 gig speeds, all 4 pairs are needed. Not only are there different Ethernet standards, but the cable itself has different standards. You will hear of terms like Category 6, or simply Cat6. The category defines things like the number of pairs in the cable, the thickness of the wire, and how tightly they're twisted. For example, Cat2 has only 2 pairs. Cat6 has 4 pairs. Cat6 has thicker wires than Cat5, and so on. Sometimes there'll be an E or an A at the end of the name. Cat5e and Cat6a are examples of this. This is where the original standard has been improved upon. Newer standards support better speeds over longer distances. For example, you can use a Cat5 cable on a 100 meg network. But if you want to run a gigabit network, you need at least Cat5e. If you want 10 gig, Cat6 is okay up to around 55 meters. But if you run Cat6a, you can have a 10 gig link that works up to 100 meters. Each newer standard is backward compatible with the older technology. For example, you can use a Cat7 cable on a 100 meg link. Your cable has a connector at both ends. This is called an RJ45 connector. This is the part that you connect to your network card or switch port. This connector has 8 pins. These line up with the 8 wires inside the cable. The wires need to line up with the correct pins. That's why the wires are color-coded. There are different color schemes you could use. This one here is called 568B. A standard UTP cable will match the wires on both ends. This means that pin 1 connects to pin 1, pin 2 connects to pin 2, and so on. This is called a straight-through cable, as the wires go straight through from one end to the other. Some pairs are used for transmitting data, and others are used for receiving. For example, pair 1 transmits, while pair 2 receives. You'll see here that I've used the terms RX and TX. These simply mean receive and transmit. When you connect a host to a switch, the switch does something very clever. It knows that pair 1 is used for transmitting and pair 2 for receiving. So it does the opposite. It uses pair 1 to receive and pair 2 to transmit. So when the host sends on pair 1, the switch receives on pair 1. The same logic is used on pair 2. The key point here is that a straight-through cable is used to connect a host to a switch. But what if you want to connect a host to something that's not a switch? Perhaps another host or a router? The pins no longer line up correctly. They are both using the same pairs for receive and transmit. So instead, we need to use slightly different cables. What we do use is a crossover cable. This swaps the pairs at one end, so transmit lines up with receive once again. This is also the type of cable you would use if you want to connect one switch to another switch. Now you're probably thinking, that's a pain. Now I have to worry about 2 different kinds of Ethernet cables and making sure I use the right one at the right time. To save you from this dilemma, we have a technology called Auto MDI-X. A device that supports auto MDIX can detect if the wrong cable is used. It can then logically switch the functions of the pins so they match the cable. The 100 base and newer standards support auto MDIX. So in the real world, you don't have to think too hard about the cable you use. In fact, crossover cables are getting pretty rare these days. If you're going to do a network exam though, you should still remember the difference between a straight through and crossover cable. When we get to 1000 base though, things change. This uses all 4 pairs of wires, while older standards only required 2. There are 2 ways this can work, which are called 1000 base T and 1000 base TX. The TX standard uses 2 pairs for sending and 2 pairs for receiving. You will need Cat 6 cabling or higher if you want to use this standard. The T standard uses all 4 ports for sending and receiving. It's a bit different to everything we've discussed so far, but it works, and you only need Cat 5e to support it. An interesting requirement in both 1000 base standards and newer is that they require auto MDIX support. The alternative to copper cabling is fiber cabling. Fiber cables use strands of glass, which are sometimes called a pipe or a core. A light pulses down the fiber strand, which is received at the other end. It works like the example here, which shows a laser following a stream of liquid. The pulsing light is another way to encode information. Fiber is often used between networking devices, like routers and switches. It may also be used in servers. I've never seen workstations use fiber, but I guess anything's possible. I'm going to take a quick detour and talk about something called duplex. Devices need to both send and receive data. UTP cables can send and receive at the same time. If both ends of the link support this, it's called full duplex. Sometimes a device will not be able to send and receive at the same time. Instead, it will send for a while, stop, and then receive for a while. This is called half duplex. These devices can still send and receive, but they can't do both at once. Full or half duplex is determined by the cabling that's used, the capabilities of the device at both ends of the link, and the software configuration. There are 2 different ways that fiber can be used. First, you can use single core only. This operates in half duplex mode, as it can't send and receive at the same time. The other option is dual core. This is full duplex, as one core is dedicated to sending and one is dedicated to receiving. Be aware though that it's easy to get the cores mixed up. If you connect the fiber and it doesn't work, try swapping the cores at one of the ends. The enterprise network will mostly use dual core fiber. This means between switches, routers, and servers. Service provider networks, like your internet and WAN providers, often use single core. Now you need to be aware that there are 2 types of fiber. These are called single mode and multi-mode. They may look the same, but they are different because of the types of light they use. Multi-mode, which is known as MMF, uses a LED light. This is not a particularly powerful light, so it is used over shorter distances, say around 500 meters or less, which makes it useful to connect devices in the same building. The LED light is also cheaper to produce, making multi-mode fiber the cheaper option. Single-mode fiber, or SMF, uses a laser light. This makes it more expensive, but it is capable of much longer distances. You could easily get 2 kilometers or more, depending on the hardware you're using. You would typically use single-mode fiber between different buildings. Or your service provider may run single-mode fiber into your building to give you WAN or internet access. Even though a fiber optic cable is made of glass, it is still flexible. You can bend the cable. Well, at least to a point. The fiber cable has a maximum bend radius. The bend radius is how tightly the cable can be coiled up before attenuation occurs. Attenuation is where the signal is degraded or lost. This does not necessarily mean that the cable won't work, but it won't work well. The manufacturer of the cable should be able to tell you what an acceptable bend radius is. There are different connectors that the fiber cables may use. Quite a few, in fact, when you remember that fiber is not just for networking. The main ones we see in data networking are called LC and SC. LC are the smaller connection types, which are usually used on switches and routers. It's common to see these in a dual-core configuration, but they can be separated into single-core. SC connectors are older and larger. They seem to be less common these days. They're more often seen in a wiring closet. Some switches will have a special port that looks empty. Some switches are made up entirely of these ports. These are made for installing a transceiver module. These can be used for different purposes, but basically, they are so you can mix and match the type of cabling you use. Different transceivers support a different cable type. This includes single-mode and multi-mode fiber. Some transceivers will support both, but they also support different speeds, like 1 gig or 10 gig, as well as different cable lengths. For example, a long cable run of 40 kilometers will need a more expensive transceiver than you will need for a 1 kilometer run. The reason that some of these switches have many of these ports is so you can mix and match which transceivers you use for the job. You can even use an RJ45 transceiver for when you want to use UTP copper cable. For that matter, you can even get a special copper cable with SFPs built in. It's called the Twin-X cable, but that's another story. The other method of communication is wireless, aka Wi-Fi. It doesn't use cabling, of course, but I should mention it quickly anyway. Wireless networks use access points. These devices are like a switch for the wireless network. Wireless devices like your phone or laptop connect to the access point. The access point may also connect to the wired network. This is how wired and wireless devices can be in the same network. Wireless is a good way to connect end-user devices. You wouldn't normally see a server or router connected to an access point. Wi-Fi does not use the 802.3 Ethernet standard. Instead, Wi-Fi uses the 802.11 standard, which was also created by the IEEE. This describes how radio waves are used to format and encode information and to get different speeds. While they're not the same, Ethernet and 802.11 do share many similarities in the way data is formatted, but that's something we can look at another time. Let's have another quick summary. Networks can be wired or wireless. Wired networks may use copper or fiber cables. In a wired LAN, the Ethernet standard is used to describe how data is formatted. It also covers cable types, link speeds, and how to encode data on the physical link. UTP is the most common copper cable. Modern UTP cable has 4 twisted pairs of wires. Some are used for sending, and others are used for receiving. The cable may be straight through for connecting devices to a switch, or it may be crossover for connecting devices to each other. Modern LANs support Auto MDIX, which enable the device to detect the cable used and adapt as needed. A full duplex device can send and receive at the same time. A half duplex device can only do one at a time. An example of this can be found in fiber cabling. Dual-core fiber is full duplex. Single-core is half duplex. If you want a short and cheap fiber run, you can use multi-mode fiber. If it has to be longer, you need the more expensive single mode. You also need to use the right transceiver in the device you're connecting the fiber to. If cables aren't going to work for you, then you can consider using wireless access points to create a wireless network. Let's go back to our Soho network for a while. We use diagrams like this to show how a network fits together. Notice that this is the logical view of the network. It doesn't show all the physical details like the number of switches used, the type of cabling and so on. It's just a simple way to show how things fit together. Imagine that the computer wants to send a print job to the printer. The printer is network enabled, so the computer can send the print job over the network. The network has several endpoints, so how does a computer know where to send the data? Could it just send a message to everything on the network and hope that the right device knows what to do? Well, this does happen on occasion. But if this happened all the time, the network would be very inefficient. Imagine if all the endpoints were sending at once. Also, this could be insecure. What if this was private information? All the other endpoints would see it. And what if there are several printers? Which one would accept the print job? Or do they all start printing? No, the print job needs to be sent only to the correct printer. But how does this happen? Each device on the network has an address. This is like your home address. Your address is unique, and it enables others to find you, contact you, and deliver packages. In a LAN, each device has two addresses. They each have an IP address and a MAC address. These two addresses are used in different ways. We're going to have a brief overview of these addresses here, and dig into more detail in later videos. Let's start with MAC addresses. Each host has at least one MAC address. To be more accurate, each network card has a MAC, so multiple network cards means multiple MACs. When the network card is manufactured, the MAC is permanently assigned. We can't change it. This is also known as the burned-in address. As each network card has its own MAC address, each MAC is guaranteed to be unique. A MAC address is used when one device needs to communicate with another device in the same LAN segment. I'll explain what I mean by this soon. Each device also has an IP address. This address is chosen by us, the network administrators. When we choose addresses, we can make them easier to remember. We also use IP addresses when one device wants to communicate with another, but IP addresses are special, as they allow us to access hosts on a different LAN segment. Imagine that our small company has been very successful and has now grown. Rather than just a single network, we have decided to create a second network. Each of these networks is a LAN segment. These are joined together with a router. This router is part of both LAN segments, so its job is to pass network traffic from one segment to another. MAC addresses are used within the local LAN segment, so when we send a message to, say, a printer in another network, we can't just use the MAC address of the printer. IP addresses, though, are different. We can use the IP address of the printer when we want to send it a message. Let's see how this works. The computer prepares a message for the printer, and it adds the printer's IP address. The printer is on another network, so it needs help to deliver the message. The computer knows that the router can help, so it adds the router's MAC address to the message and sends it. The router receives the message and strips its own MAC address off the message. In its place, it puts the printer's MAC address on instead. The router then forwards the message to the printer. This may raise a lot of questions for you, but don't worry, we'll look at how this works in more detail another time. For now, just remember these things. Hosts have a MAC address and an IP address. A MAC address is used only within a LAN segment. An IP address can be used within a LAN segment, but is also used to pass traffic to a different LAN segment.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.